Welcome back. Section 4.4 span. Here on we'll write simply plus and dot instead of O plus and O dot. Keeping in mind this plus is not the same as standard plus, it is vector addition. This dot is not necessarily the standard multiplication, it is scalar multiplication. Definition: let V plus dot be a vector space and let S be a set of n vectors v1 through vn, a set of vectors from V. The set of all vectors in V that are linear combinations of the vectors in S is denoted by span of S or span of v1 through vn. So what does this set mean? You take a linear combination of v1 through vn, put it in a set. Take another linear combination, put it in it. Remember, what is linear combination? Scalar times this plus some scalar times this plus scalar times this. So you are taking all possible linear combinations, collecting them, that is called span of S. If S is the empty set, that is, you see, your set S can be a priori empty for all you know, then by convention, that is convention means agreed upon, decision, right? If S is empty set, then we say span of S is equal to the set of zero vector, just one vector. If S is an infinite set, so you see here I gave you a finite set. What happens if you have infinite set? Then we define span of S to be consisting of all finite linear combinations. So you have an infinite set, say, then take all finite linear combinations and put them in the span of S. Okay? For example, so suppose I take a set of 4 matrices, one here, one here, one here, one here. Everybody else is 0, notice. This is a subset of 2 by 2 matrices with real entries. Now what is span? Well, it is a set. Notice I've written set symbol, that's important. A1 times this matrix, A2 times the second matrix, A3 times the third matrix, A4 times the fourth matrix, where A1, A2, A3, A4 are all real numbers. So, linear combination of these 4 matrices. You keep putting them together in a big set. That is your span of S. Well, when you actually simplify it, it is same as A1, A2, A3, A4, the matrix, where AIs are from real. So this set is actually the entire set of matrices, 2 by 2 matrices. In other words, these 4 matrices alone span everybody here. Okay, so that's the point of it. You notice the meaning, English meaning of the word span. Span means the reach. So these 4 matrices have a combined reach of the entire set of matrices, 2 by 2 matrices. I hope it's clear, okay? So what is span? It is collection of all linear combinations that you get from your given initial set. Here is another example. Consider 3 by 2 matrices. Okay? So 3 by 2 matrices, I've chosen only 3 matrices. One here, and one here. Everybody else is 0. So what do you think is the span? So A1 times first matrix plus A2 times second matrix plus A3 times third matrix, where A1, A2, A3 can be any real number. Yeah, can be any real numbers. Well, when you simplify, what do you get? You see, A1 gets you a slot there, A2 gets you a slot here, A3 gets you a slot there. All right. So, you don't get all the matrices. For example, you are required to be zeros here in the span, but these three entries can be any real number. So you do not get entirety of M32, but you get something, some substantial subset, okay? Because A1, A2, A3 can be any real number. So you get infinitely many matrices, except you don't get the entire set of matrices. I hope the picture is clear. Here is an example. Let P be the set of all polynomials with real coefficients in variable t. So you're looking at all polynomials. We know P is a real vector space. Let P3 be the subset of P consisting of all polynomials of degree less than or equal to 3. Since P3 is not, now note P3 is non-empty because here is one polynomial. Degree less than or equal to 3. In fact, degree equals 3. This polynomial is in P3. Suppose you have two polynomials f and g of degree 3 or less. Then f can be written a naught a plus a1t plus a2t squared plus a3t cubed. That's f. Likewise, g may be written b naught plus b1t plus b2t squared plus b3t cubed, where a3 or b3 could be 0. They are allowed to be 0 because my degree is less than or equal to 3. Now notice f plus g. If I add these two polynomials, right? If I add these two polynomials, look, constant gets added to constant. Linear term a1 plus b1 t, a2 plus b2 t squared, a3 plus b3 t cubed. So you know that P3 is closed under vector addition. Suppose you take R any real number, H any polynomial. Then R times H is R a naught, R a1t, R a2t squared, R a3t squared. That's also a polynomial of degree 3 or less. Therefore, P3 is closed under scalar multiplication. So what have we shown? P3 is non-empty, it's closed under addition, it's vector addition that is, and it is closed under scalar multiplication. So this means P3 is a subspace of P. All right. Now consider the set of 4 polynomials. First polynomial is just 1. Second polynomial is just t. Third polynomial is t squared. Fourth polynomial is t cubed. So these are 4 different polynomials from P. Moreover, these polynomials are each of degree 3 or less. So they are in P3. Consider span of S. Some number times first polynomial, number times second polynomial, number times third polynomial, number times fourth polynomial, where these numbers could be any real numbers. So what do you get? Span of S is all of P3. You get all the polynomials of degree 3 or less. Okay, so here is an important theorem. Let V plus dot be a real vector space and S be any subset of V. Then span of S is a subspace of V. What does that mean? Span of S is a vector space in its own right. Okay? What does that mean? Remember, how do you show something is a subspace? All you need to show is that it is non-empty, it is closed under vector addition, it is closed under scalar multiplication. So proof, if S is the empty set, then by convention span of S is the 0 vector. That is, if S is empty. Now 0 vector, the set of 0 vector we know is a subspace of V. We saw this in our previous section 4.3. Now, on the other hand, if S is non-empty, then for any vector V in S, we see that 1 times V, right? You have a because S is non-empty, you have a vector in it. 1 times that vector is in span S, because that's what span is, all sorts of linear combinations. So 1 times V is a vector, which is V, it is in span S. So you know for every vector V, it is in span S. In other words, the S itself is contained in span S. So you know span S is non-empty. Now let's take two linear combinations in span S. Summation I going from 1 to n ai vi and summation I going to from 1 to n bi vi. These are two vectors. You see, these are finite sums, linear combinations, two vectors in span S, where we have chosen v1 through vn from S. A's are in R and so are B's. Okay, I haven't written it, but B's are in R as well. Now what if I add these two? If I add these two, notice I can simply add AI plus BI times VI. All I'm doing is distribution, commutative, associative, and such things. So you see, when I add these two, I get another linear combination of VI. Therefore, it belongs to span S, which means span S is closed under plus. We have used associativity, commutativity, and even distribution of scalar multiplication. Now, suppose you take any real number and any linear combination in span S. Then R times the linear combination is, you see, distribution R goes in to each AI, which means that is another linear combination, therefore is in span S. That is, span S is closed under scalar multiplication. So we know span S is non-empty. It is closed under vector addition. Now we have shown it's closed under scalar multiplication. So it is a subspace of V. All right. We have proved the theorem. Let's continue in the next video.